Example 6. Example 6. Find the x coordinates of the relative extrema. So are we looking for x coordinates or y coordinates? Yeah, x coordinates. Okay, it's important, right? We have two functions. The first one is t of k. T is the name of the function. K is the independent variable. Are we on cusp alert? Yes, we are. In fact, if we were going to take the derivative, we would write the cube root of k squared is k to the 2/3, and there's your cusp alert right there. So we already know that there's going to be a critical value where the derivative is undefined at k equals what? What's the root of k to the 2/3? 0. Yeah. We already kind of know that. The domain of t is all real numbers. Would you agree? The domain of t is all real numbers. You could take the cube root of any number. It's going to be squared anyway, 2k minus 1. So, yeah, so now we need the critical values. So t prime of k, we're going to have to use the product rule. So we get 2/3 k to the negative 1/3 times 2k minus 1 plus k to the 2/3 times the derivative of 2k minus 1, which is 2. Now, because we are after a full-fledged factored version of the derivative, rather than keep it as two terms and bring the negative 1/3 to the denominator, I'm going to go ahead and factor out least powers right here. Factor out least powers. I've got it looks like a 2 that I can factor out, and I got some k's that I can factor out. So we'll factor out a 2k. Beefy brown bracket.
Well, you wouldn't want to factor it out.
What's that?
Would you not want to factor out k to the negative 1/3?
Yeah, I was going to come back and pick the exponent later. Yeah, what I did actually forget to talk about the exponent. What exponent should we choose? Which is smaller, negative 1/3 or 2/3? Yeah, negative 1/3. Thank you. I would have noticed that as soon as I get to the next step, because now I'm trying to factor out something. So when I factor a k to the 1/3, negative 1/3 out of itself, I'm left with 1. So there's left with the 1/3 there. You want to factor out the 1/3 as well? Let's factor out the 1/3. If we're factoring out least powers, we should factor out least numeric factors too. That way we won't be left with a factor. We can factor a 2/3 out. So when we factor it out of itself, we're left with the 1. When we factor k to the negative 1/3 out of itself, we're left with the 1. So we're just left with the 2k minus 1 factor. If you didn't factor out the 1/3 like I just did, adjusted it, you would have a complex fraction in your answer, and you would just simplify it later. But notice we're left with 2k minus 1. Now, what are we left with when we factor a 2 out of the second term? We're left with 1. But when we factor a 1/3 out, we're left with 3. Yeah. Because it's 1 divided by what you factored out. 1 divided by a third is 3. And we're left with k to the what power? 2/3 minus negative 1/3 is 1. There you go. That cleans up super nicely. And again, this is the quickest, fastest, most efficient way to get it down to a single term. So now we're left with a 2 in the top, a 3 in the bottom. The cube root of k jumps down there, and there is our critical value that we were anticipating on cusp alert. And notice what's left in the top. We have 3k plus 2k, that's 5k minus 1. There's your full-fledged factored version of t prime. Now, critical values, we're going to use it twice. So t prime of k equals 0. If you set the derivative equal to 0, you've already earned the check. You don't need to go ahead and then separately set the denominator equal to 0, or the whole expression in the numerator equal to 0, because you might be able to look at that linear factor, 5k minus 1, and just realize that k equals what? 1/5. Okay? So that's why it's worth just saying t prime equals 0. Of course, if you want to just say the numerator is equal to 0 and do the algebra involved, that's fine. T prime of k equals d and e. That's when the denominator is 0, and that's when k equals what? 0. Now remember, if you ever get a number for both of those that's the same, do you keep it or throw it out? If you get 0 over 0 in your derivative, you toss it out because it's not a vertical tangent. It's where the derivative is undefined. Well, the function is probably going to be undefined there as well. All right, so at this point we got two values, two critical values, and we're trying to find the x coordinates of the relative extrema. Do we box them up and walk away? Is every critical value a local max or a local min? No. So now we just need to make sure. It could be that they're both just critical values that are horizontal tangents. So let's make a number line chart. We'll have K. You saw that coming. K and T prime. 1, 0, 1/5. All right, a number to the left of 0, -1. A number to the right of 1/5, 1. Yeah. A number, now if I choose a number that's less than a fifth but greater than 0, I probably still want to make it a factor of 5, because when I plug it back in, I'm going to have to multiply it by 5. So how about 0/5, 1/2? I'm going to choose 1/10. You can choose whatever you want. Okay. That'll work. Super. That's the beauty of this. You can choose any number. Now I'm going to plug it back in up here to my full-fledged factored version of the derivative, my triple FF prime. Full-fledged factored version. -1. What do I get when I plug in a -1 in? In the top I get a negative. In the bottom I get a negative. A negative over negative is positive. Plug in a 1/10. On the top I get 5/10, which is a half. -1 is now negative over the cube root. The bottom is going to be the sign of whatever k is. Do you see that? Because the cube root preserves the sign and the 3 is positive. So I'll get a negative over positive, which is a negative. And if I plug in a 1, I get a positive over positive. Are they both, in fact, local extrema? Yes. So it says to justify. So very quickly here, T has a local max at x equals 0, since T prime changes from positive to negative at x equals 0, or k equals 0. I guess we should say k. Let's talk about that. What if you're so used to using x's that in your justification you put x instead of k? Technically it's wrong, but you would probably be granted amnesty, because using x is still kind of referring to the default independent variable, and there's no confusion. There's nothing else in this problem we're calling x. So that would probably be forgiven. T has a local max at k equals 0. Oh man, we don't want to do it again. What if you accidentally call a minimum a max? Is that forgiven? No. At k equals 1/5. Yeah, well, because I was saying it out loud again. Since T prime changes from negative to positive at k, I wrote x again. I said k, I wrote x. Okay, there you go. Now, because 0 was the cusp, and it was a local max, you can actually come back over here. You can kind of amend your picture, as Rapp was saying. You could actually do it like that and do something like that. Now, we got to be careful here. We can't turn the corner when we come up. It's coming in from, it's positive everywhere to the left, so you just redo that. Coming up like that, cusp, and like that. So that's what the graph looks like, something interesting. And, of course, you can place it vertically on the graph if you want by finding actual y values. All right, letter B, j of x. The function's name is j. The independent variable is still k. I said x, but it's k. In fact, do you want to just call it x so that we don't get confused? Will that work? Sure, let's do it. Let's just write it down as x. What's the domain of j? It's also all real numbers. Are we on cusp alert? Yes, we are, because it's k to the 1/3. And we already know that we're going to have a critical value at what? K equals, or x. See, now I'm writing them down. I changed it to x, and now I'm writing them as k again. We're going to have a critical value at x equals 0, and it's going to be a vertical tangent. It may be a local max, local min. It may just be a vertical tangent cruising through infinity. All right, so here we go. J prime of X, J prime, the new album by J prime, featuring implicit lyrics, plus X to the 1/3 times 2. Factoring out least powers again, yeah? So much fun. Let's go ahead and factor out the 1/3 and an X to the negative 2/3. That's the smaller of the two. Beefy brown brackets. What are we left with in the first term? 2x minus 1, or 2k minus 1 if you're embracing the k's. Plus 2x to the 1/3 minus negative 2/3 is to the first. And so now this step here is cleaning it all up. 2x plus 2x is 4x, so we get 4x minus 1 on the top, 3 cube root of x squared in the bottom. Least powers. Subtract exponents. I forgot to put a factor out of 1/3. I saw some squinting eyes, and that's good. When I look out there and I see y'all squinting, it means you're trying to give me the benefit of the doubt, but you're in your mind saying, he messed up again.
Teachers and students, please find this interruption. Just a reminder, students, if you were absent yesterday for any reason at all, please make sure you stop by Ms. Norris's office in the back office sometime today to pick up your report card.
All right, when you factor out a 1/3, you're left with a 3 times the 2 that's there is 6. If you distribute, 1/3 times 6 is 2. So that I was supposed to get a 6.
Gabriel Gaona, Andrew Cano, William Anderson, Jesse Mateus, Samuel Johnson, Edson Holler, Pedro Flores.
Thank you for catching. You were the one with the squinty eyes. You were trying to figure it out. Yeah, sorry.
Morgan Burley, Janie Aguilar, Tiffany Tron, Tyler Bilkey, Timothy Jensen, Brandon Knightley, Sativa Rodriguez, Abner Tanner, Kaylee Young, Jalen Patel, Santos Martinez, and Dawson Smith. Congratulations, you guys, on the perfect attendance for the second 6 weeks.
Also, teachers, please turn on your TV to channel 4 for these morning announcements. You may also watch them at nbhstv.com. Thank you.
Okay, so just doing a little bit of work while they're talking on the announcements. Congratulations to all those who are always here. There's a treat for you. You factor out a 1/3 and you're left with the residual 3 plus or times the 2 that was there, you get the 6. So that's where I messed up, which is going to be very significant because that ends up changing your critical value, because now 6x plus 2x is 8x minus 1. The denominator is that. Setting j prime equal to 0, that's when the numerator is 0, that's 1/8. The denominator is undefined when x is 0. Those are your two critical values. We were all over x equals 0 in the beginning. We spotted him on the cusp alert. Set up your number line, and now it's time to plug in. Notice the denominator is always whatative. It's always positive. That's nice. You don't have to plug into the denominator. The sign of j prime is determined exclusively by the numerator. Pretty sweet. Save a little bit of time. Plug in a -1, you get -8 minus 1 is negative. Don't tell me, I don't care. Plug in a 1/16, you get 8/16. That's a half. Half minus 1 is negative. Ooh, did it change signs? Nope. Plug in a 1 and you get positive. So it turns out, if you want to remember what this looked like, there was a vertical tangent at 0. So it's decreasing. So that's going to look something like this. It's going to go vertical right there. But instead of boing, bouncing out like a cusp, what does it do? Yeah, it continues back like that. And then it, so let me do that again. It goes vertical, and then it comes out like that. So it looks something like that. So not every critical value is going to be a local extrema. All right, so then the justification would just be J has a local what? Min. The local min at x equals 1/8. There's a check, essentially, since J prime changes negative to positive. Where, y'all? In France? No, I don't think so. I was writing the word where. At x equals 1/16 or 1 or 1/8? Yeah, 1/8. Remember, it's real easy to come back in here and use one of your test values. So make sure that those critical values stand out. And that's it right there. All right, let's do example 7 and we'll be done for the day. Piecewise functions. Always the exception. Okay? They're the hybrid monsters. They're defined to be anything. They're Frankenstein's monster. We're looking for the relative extrema. Is that x values or y values? Y values, yeah. If you have a function like this, you might just want to do what? I would graph it, yeah. Let's go ahead and review how to do that. This one looks like it's going to be pretty easy. Because everywhere to the left and right of 1, it's going to be the line x plus 3, which has a y-intercept of 3, and then it's up 1 over 1. So it looks something like this. It has a slope of 1, sorry. Oh, now I'm going too far back. Let me start over. Hey, when you have a piecewise function, you might just want to graph it. Has a y-intercept of 3 and a slope of 1. So up 1 over 1. There we go. We'll just do it like that. Now we'll just call this point 2. And we'll come in here and we'll put like a little open circle. Kind of swipe out a little spot. Like that. There you go. And then you come back in and connect it. Or just draw it with this open circle to begin with. Do we know what the y value of the open circle is? What point did I just swipe away? 2, comma. What am I? I'm an idiot. Why are we even doing this? Yeah, I'm an idiot. Yeah, it's 4. Did you? Before I did it. It's easy to do. Yeah. This is a pretty simple little piecewise function, but so tempting to make some psychological mistakes. Pathological psychological mistakes. Yeah, so the limit as x approaches 1 is 4, okay? And then we're explicitly saying that when it is 1, we're going to call it 2, which will be right here. So, of course, the function is not continuous at x equals 1. There's a what there? A hole. Can we use the first derivative test on this one? Does f prime, the slope, change signs on either side of 1? No, it's positive to the left, it's positive to the right. So if you did try to use the first derivative test, if the derivative is positive to the left and right, it would be a relative what? Max, min, or neither? Neither. So remember that the first derivative test only works for continuous functions. Do we actually have a local max or local min at 1? Here's the y value at 1. Immediately to the right, we have values that are bigger. And immediately to the left, we have values that are bigger. Therefore, 1 is a local min. Yes, f has a local min at x equals 1 of y equals what? 2 or 4? 2. Good. Remember, that's for the local extrema. You cannot justify by the first derivative test. You can't say since f prime changes from negative to positive, because it doesn't. It's positive on both sides. So the first derivative test only works for continuous functions. If you had to justify, what would you say? You would say something to the effect that since immediately to the left and right of 1, the function f has y values greater than 2. But you're probably not going to have to justify that. So local extrema can occur at discontinuities, but the first derivative test does not apply. It only works for continuous functions. We will finish tomorrow pretty easily, and that means that the worksheet will be due on shucks darn Monday. That gives me more time to remember to make an e-backpack folder. Did I say remember or forget? Yeah, we'll quiz Monday.